running here as we speak from his teaching, so will join a little bit later. And next week we will have Giacomo Lanzani, who is presenting non-linear fixed points and stationarity economic applications. All right, so yeah, Moritz, go ahead.
All right. Well, thank you very much for having me and for this for the invitation and the nice introduction, Julia. It's good to see you, the ones that I see on Zoom. So the title of the paper is a mouthful here: simple contagion dynamics in tree-like networks, but that's very descriptively what it is, right? So when we first discovered Zoom at the beginning of the COVID epidemic, the one epidemic that was allegedly spreading faster than COVID was the epidemic of econ papers on COVID and epidemics. And so everybody was discovering the simple contagion model, the susceptible infected model. And, you know, of course, some economists had discovered this before. The BAS model, the classic model of product diffusion, is an SI model, right? And so Kramer's model of precautionary behavior in a pandemic is a behavioral model of such a contagion, where people choose their social activity to to go about their daily lives, and at the same time trying to avoid, in his case, the AIDS epidemic. And then Banerjee's model of rumors is a model where a rumor diffuses through a population, and by the timing of when you hear about the rumor, you're trying to infer something about the veracity of this information. All of these papers, including, I believe, most or maybe even all of the more recent wave of economic epidemiology models, are random matching models. Right? So the social structure is a random matching model. I bump into people randomly. Right? And so, at some level, you might say, right, that's sort of one way of thinking about social interaction. Then again, of course, we keep bumping into each other, right? So this is not the first time I'm bumping into Evan, and in the random matching model, I'd only bump into him once, right? And so, there's a question: what does this network structure imply for contagion models, right? And so, at the normative model, how would you speed up the diffusion of a good epidemic, right? So if some innovation is spreading through the market, like in BAS, or flip it around to a bad epidemic, how do you slow it down? I mean, so what of these COVID non-pharmaceutical measures that we were all suffering under for 5 years, how do they quantitatively change the dynamics of the epidemic? And at a positive level, how does the network structure speed up or slow down the spread of a rumor? And so those are the broad questions here. The contribution of the model, so we're going to sort of model these contagion dynamics on configuration networks, and so we are not inventing configuration networks, right? We're not even introducing configuration networks into the econ literature. That has been done, but still we're pushing the model of configuration networks, right? And so if you haven't sort of seen the model of configuration networks, the single most important thing I want you to take away from this paper here is just how tractable these networks are, right? And so here are some properties of these networks. They look like trees as the number of agents goes to infinity. That's realistic because it matches the small worlds feature of many social networks. And it's what makes the model tractable, right? So you'll see. It's a very flexible model, and so even though the networks look like trees, they can match important salient features of realistic networks. In particular, we can match any degree distribution, right? So if you want to have your model feature super spreaders, that is a parameter of the model. If you want to think of your model as a directed network rather than an undirected network, maybe like in a social network like Twitter, it's easy to add. If you're concerned about clustering, the fact that the friends of my friends tend to be friends with each other, well, that would mean that the network isn't literally a tree, and yet it's a simple thing to add to the configuration network. Right? So when I say they're tree-like, on a macro level, they look like trees. On a micro level, they can have clustering. If you think of, I was talking about the networks in contrast to random matching. Um, if you're worried about networks that evolve over time, in the extreme case, random matching, you want to sort of resample links, it's easy to add homophily, easy to add, right? So they can match most of the salient features that networks folks are emphasizing. What do we show? Well, we characterize infection rates as a function of time via one-dimensional differential equations. And so the way I measure tractability in the model is by the dimensionality of the differential equation that describes the dynamics. Right? And so the beauty of one-dimensional ODEs is that they're very amenable to comparative statics. Right? So we can compare the contagion rates, the infection rates in these networks across networks. And so what we find is that undirected links, clustered links, fixed links, they all slow contagion. And so we can rank all these networks that I was talking about above. Uh, so this is, the network architecture has an effect, and how large, and we can also measure the size of the effect. Right? And so
So
particular,
Moritz, if I could
yeah,
interrupt just ever so briefly, I wanna ask. So you're emphasizing the simplicity of being able to do all of this with one-dimensional ODEs. Could you give us a
yeah.
sense of sort of the kinds of extensions that would require sort of more complicated ODEs? And if now is not a good time, feel free to punt until later.
Um, so the traditional model in mathematical epidemiology with clustering requires a two-dimensional equation. A model that has both bilateral links and triangular links, okay, that doesn't make sense yet. That requires a multidimensional differential equation. So, it has its limits. And so we're basically showing what can we do with one-dimensional differential equations. And that's what I'm emphasizing. But in in writing the paper, of course, we've reached the limits of this approach. All right. I was saying network architecture, it matters. We can say in which way it matters, and then we can say it doesn't matter all that much. Right? That's the third bullet here. In regular networks, the effects are small, they're less than 1 degree. So yes, clustering slows down the contagion, but cutting one link for every node, that slows the contagion even more. Right? So that's saying that if people have a lot of degrees, then maybe network architecture is not so important. If people have few degrees, well, then one more degree is maybe a big deal. And so in sparse networks, the network architecture does matter. The main model is the simple mechanical contagion model from epidemiology. And well, then we are sort of pushing the model in applications to behavioral models of epidemiology, much like I would say, the second wave of economic epidemiology. Right? So we'll look at participation in harmful and helpful contagions. A harmful contagion is one where the COVID virus spreads and people participate in the COVID contagion by not taking a vaccine, right? And so you opt out of the epidemic by getting the shot. Whereas with a helpful contagion, some innovation is spreading and you're investing. So maybe AI is spreading across the business world, and you're investing into your organization by hiring fancy computer scientists or maybe economists, I don't know, that can then help your organization adopt this new innovation when it comes along. Right? So that's the participation application, and then we'll have an application to experimentation. And these economic applications, they then allow us to talk about behavior, so we can rank equilibrium actions, vaccination rates, and we can talk about welfare. Right. So here's okay. So it's not a proper literature review because, in a way, too much happened there in economic epidemiology. So I'm quoting here just survey papers. And so those are quotes here that sort of emphasize the importance understanding social structure better and modeling via a network. And so the epidemiology literature, the economic epidemiology literature is based, I believe, totally on random matching, right? And so here these surveys, they're saying, well, that means we don't know who these contacts are, who we're matching with, because they're just randomly drawn, right? And so McAdams is saying here, I think the literature should be shifting in the direction of networks, which is what this paper is doing. The math literature has done this already. So the mathematical epidemiology literature has studied the infection dynamics on networks, both in heuristic and in rigorous exact models. So the seminal papers are there by Waltz and Miller that characterize the dynamics on undirected trees. And so the current textbook here by Kiss et al. Describes the challenge in sort of pushing this analysis to study other aspects of networks like clustering, right? And so that's the direction in which we're pushing it. There's also other differences, right? So this is a math literature, so they wouldn't do comparative statics, right? That's just not the kind of question they would ask. So there are similarities on the level of the math, but the questions are eventually different. All right, so here's the model. So this is the model of networks, right? So the first block here is already the full rigorous model of the configuration network, right? So these three bullets here are enough, right? So the undirected configuration network has a finite number of agents. I is our number of agents. And then we're going to generate this network randomly in two concept step. Each agent draws a number of, stubs, right? So n is the number of stubs of an agent. We'll always assume that the expectation of that random number is finite, right? So that's the first step. Agents draw stubs. And now that every agent has a random number of stubs, we randomly connect pairs of stubs into links. And there's going to be undirected links because we're talking about the undirected configuration network. And so what I mean by randomly connect pairs is that I'm like, and then when I draw another random stub, I could draw a stub of another stub of mine, and then I'd be sort of holding my own hand, right? So that wouldn't be a link in a network sense, because links in networks, they go from one agent to another agent. Okay, and so that would be a self-link. Another thing that could go wrong is that we could have a multi-link, right? I'm already linked to Evan, and then by chance, I'm going to link to him again. That'd be a multi-link. And then it could be that there's an odd number of total stubs, and then there's going to be one left over at the end. And what I'm going to do is I'm just going to throw these away. Right? So I generate all these links according to this two-step recipe. And then if I formed any of these sort of exceptional degenerate self, multi, or leftover links, I'm keeping the network, but I'm throwing away these links. So in the math literature, this is sometimes called the discarded configuration model. And so there is an alternative. You could have the so-called repeated configuration network, where you say you don't throw away the links, but you throw away the entire network drawn. You just redraw the network. So basically conditioning your network on not realizing any of these self, multi, or leftover links. Right? But we're doing the discarded model. Right? So that is our baseline model, the undirected network. And then we'll study two variants of that. Right? So the directed network, right? The undirected network has a bar on top of it because, the bar doesn't have a direction. And the directed network has an arrow on top of it because, an arrow has a direction. So, as in the undirected network, in the first step, each agent draws a random number of, okay, so now there's going to be pairs of in stubs and out stubs. Now my stubs are labeled. And then in the second step, I draw a random in stub from some agent and a random out stub from some agent. And then I connect the in stub and the out stub into a directed link. Right? So here would be the in stub of J and the out stub of I. They connect into a link from I to J. Right? And so then I'm going to get a network where we can have a link from I to J, but not from J to I. And if there's a lot of agents, then it's very unlikely that we have a bidirectional link. So that's our directed network. And then the third kind of network we're going to be studying is the triangle network. And so the triangle network has a little hat on the top because it looks like a triangle. And oopsie, wrong direction. So here the way we're going to generate triangles is by saying that instead of drawing stubs and connecting them into pairs, each agent draws stub pairs, but not like in a directed network where it's an in stub and out stub. Like every stub is both in stub and out stub. So they are undirected. And then what I'm going to do is I'm going to take a stub pair of one random agent and then another random stub pair of some other agent usually, and then a third stub pair, and then with three stub pairs, I can connect them into a triangle between agent I, agent J, and agent K. Right? And so in the direct and the triangle network, I can also have these self-links, multi-links, leftover stuff. And just like in those models, I'm going to discard them. And so these are the models on which I'm going to study the contagion. Right? And so let me just give you the model of the contagion here. It's the one that you probably have been anticipating. The continuous time model starting at time zero. At time zero, we seed some nodes with some probability epsilon. I'm going to write it as 1 minus S0. So the infected ones are X and the susceptible ones are S. And it's going to be easier to keep track of susceptible ones. So initially S0 of them are susceptible and then the rest are infected, right? So those are the people who, caught COVID by bitten by, I don't know, the bat or something. Then they infect each other at some rate that we normalize to 1. Right? And so when I say they infect each other, it's not random. It's not a random matching model, but I'm infecting my neighbors at rate 1. Here's an important assumption here. When I turn infectious, so I'm turning infectious at rate 1, when I turn infectious, I infect all my neighbors at the same time. Right? So that is an assumption that will turn out to be irrelevant for the tree models, for the undirected and directed trees. It will turn out to make a difference for the triangle networks, right? So the idea for triangle network then is that once in a while the three of us meet, and then if I'm infectious, I'm going to give it to the two of you. Right? So that's this assumption here. So I want to flag it right away because that's where we're departing from the mathematical epidemiological literature. And the rest of the slide is notation, right? So the capital letters here, they're random variables. So it's the state of agent I at time t. And so capital XIT denotes that I am infected at time t. So it's a 0, 1 binary variable, and SIT is just a negative, is 1 minus that. And that denotes that I am susceptible. And then lowercase letters xt here, that's the expectation that a node is infected at time t. And I'm dropping here the subscript I because I'm thinking of I as a random node. So I'm sort of implicitly taking expectation over I as well, but they're all symmetric. So that's not really an expectation. In expectation, they're all the same. And yeah, so S0 then here is the expectation that you are susceptible at time 0. I'm going to stop here for a moment and pause for questions because this is the entire model.
I think maybe it's just useful to clarify, confirming that so this is an SI model, so there's no recovery once you're infected, you're always infected, right?
Excellent. Yes. So so I would say that this is the baseline model, but the first model that I learned was the SIR model, right? And so in the SIR model, there's another process by which infected people recover at some other rate, right? And so, we could clearly extend the model in that direction, and we'll do it on some slide, and most results will generalize to the SIR model. But I think, so I view the SI model as the baseline model, right? So I think recovery is very reasonable in many applications, but I view it as an extension of the baseline model.
And maybe one more just sort of quick note of clarification. So this S naught that you have there, that's, I guess, the probability that you are not infected at time 0.
That's exactly right.
All right. And should we be viewing that as something that's very, very close to 1, or is this a parameter you're going to play with?
Yeah, I'm going to think of that as a number that's very close to 1 and the infection probability as a small probability, but that's not going to matter, right? All the results are true for any value of that. All right. Okay, let me proceed then. So here's an important thing to know about networks, the friendship paradox, right? So this is a fun party trick, if you will. I mean, think of how many friends you have, how many social contacts you have, how many people you might get COVID or new ideas from. Um, and that's some number, and for a random personal population, it's a random number. And then think about a random one of your friends, and think about how many friends your friend has. And the friendship paradox says is that for the typical agent, the typical neighbor of the agent has more friends than the agent herself, right? So I is my typical node, Iris, and her typical neighbor is J, John. And John tends to have more friends than Iris, which, sounds like a paradox because, those are random people. But the way that Iris and John are different is that Iris was picked randomly out of the population, whereas John was picked randomly among Iris's friends. Right? And so when I'm sort of following one of I's links to find another agent, well, I'm more likely to find a high degree agent than a low degree agent. Right? And so that's why a typical neighbor has more friends than the typical node. And so in the configuration model, we can make that relationship precise. Right? So n prime is the random degree of the typical neighbor, John, and it exceeds the typical degree of the typical agent, Iris. Right? So that's this ratio here, exactly by the ratio of the degrees. Right? So that's coming straight out of the recipe for the configuration model, right? And so that's going to be important, or important, right? So we need to sort of keep track of that, right? It's more of a housekeeping thing. Wrong direction here. Okay, some examples here. In a regular network where every node has the same degree, yeah, well, okay, so there's no effect, right? Because everybody has the same degree. In maybe the most famous configuration model, the Erdős-Renyi model. The Erdős-Renyi model says that any two links are connected with the same probability independently. And then if you take the number of agents to be large and the probability, you scale down the probability of any two agents being linked at the same rate so that you fix the expected number of links, then the degree is Poisson distributed, right? So just the limit of binomials converges to a Poisson. And then the neighbor has exactly one more degree than yourself stochastically. Because, how is the neighbor different from the random node? Well, the neighbor is connected to you, right? So that's the one additional link that the neighbor has. Other than that, the neighbor looks just the same because all the links are realizing independently. Right? So for Poisson, the friendship paradox is exactly this number 1 here. And if we're thinking of super spreaders, right, so if you think that degree distribution has a fat tail, so if we have this Pareto distribution here, then it's simple to compute just from the math up there that the neighbor distribution is also Pareto, but with a coefficient that is 1, but it's smaller. Yeah, right. So it gets fatter, right? So in particular, what can happen is that we said n has finite expectation, but n prime might have infinite expectation, right? So, and that's the way that the super spreaders are going to, accelerate the infection here, right? Because there's people with very high degree out there, right? And that's captured by by this coefficient in the Pareto distribution. All right, friendship paradox, that was important. And so here's the important feature why these configuration models are going to be so tractable. As the number of agents goes to infinity, these networks, they all locally converge to trees. Right? So when I mean, so this sort of a bunch of math hidden in the air quotes here, that and what I mean by locally converge to tree is that fix a node and then fix a radius around this node, right? So only look at the network of the subnetwork of agents who at most are sort of steps away from your root agent, and then this local network is going to look like a tree as I goes to infinity, right? And so the undirected configuration network is going to look like a tree, like a random tree that has n neighbors. Each of these neighbors has n prime minus 1 second neighbor. So the n prime is the random degree of the random neighbor, and the minus 1 comes from the fact that when I'm thinking of my second neighbors, I'm not counting myself. Right? I'm only counting the distinct second neighbors, right? And so then each of these has n prime minus 1/3 neighbors, etc., etc. Right? And so in the directed network, I have n neighbors, and each of them has n prime second neighbors, because in the directed network, as I goes to infinity, the chance that my neighbor links back to me and wastes one of their links on me, well, that's going to go to 0 as I goes to infinity, right? And so the undirected tree here, so if n is, if the network is regular with degree 4, the undirected tree is the one that we see here in the middle, and the directed tree is the one that we see on the left. And so the tree-like model, that is the clustered triangular configuration network, well, that converges to what I'm going to call, it's a bit of an oxymoron, a triangle tree. Right? So that's the thing that we see on the right here. So this is something that locally looks like a triangle. Right? So our node here has lots of triangles that connect them. But on a macro level, it looks like a tree. Right? So we have these little clusters on a local level, but then beyond that, the triangles spread like a tree. So this is the way that the finite networks that are very complex and that would be hard to describe, they converge to something that's very tractable as I goes to infinity. All right, so here is the analysis of the spread of the contagion. I'm going to start with the benchmark of random matching, because that's where the literature is coming from. So in the random matching model, so intuitively what I'm thinking about is a model where the network is redrawn at every instant in time. Right? And so then I still have my degrees, and I still have the degree of the neighbor that I'm drawing at any instant in time. The more natural way to think about the random matching model is that n is the matching rate, right? So it doesn't really make a lot of sense to think of this as stubs in the random matching model, but okay, so we could do that instead. And so here's the analysis. So we got to solve the model at the level of the random neighbor, because the typical agent is well, what we just showed in this lemma here is that these models are all self-symmetric at the level of the random neighbor. The random neighbor is in a way the typical person. Right? The random node is a bit different, because the random node has fewer neighbors. Right? And so the A here is the infection rate of the typical neighbor. Right? So take any random edge and the person at the end of the edge, and AT is the expected infection rate of that person at the end of the edge, right? The infection rate of the random neighbor. And what's the chance the random neighbor is infected? Well, what's the chance he's not infected? He's not infected if he didn't start infected. That's the S0 here. Well, and then he shouldn't have gotten infected by the contagion process between time 0 and t. Or random neighbor has degree n prime up here, and so theta t to the n prime, that's the chance of not having been infected by my n prime neighbors. Theta t is the chance of not having been infected by one of my neighbors. And what's the chance I'm not infected by one of my neighbors? Well, at every instant in time, each of my neighbors infects me with probability AU, right? So that's where the model is symmetric, right? So this is the same AU from the AT here. And the chance that I survive, my susceptibility survives from time 0 to time t, well, at any instant in time, I could get infected with chance AU. So I integrate it up, take the exponential, and that's the chance that I haven't been infected up until time t. Right? So
So,
80
so
then
Moritz,
here. Yeah.
I have a question on this slide. So I'd like to understand why you're not keeping track of infection rates separately by degree. Because if I think about, like, let's say I've got a population, half the population has degree 2, half the population has degree 6. The people with degree 6 are going to get infected faster. A higher fraction of the, like, say, 2 periods go by, higher fraction of the degree 6 people are going to be infected than of the degree 2 people, right?
Yeah.
And so then I care whether my friends have degree 6 or degree 2, right?
Yes.
And so it's not just enough to think about, my degree. I also need to think about, well, what's the degree of the people that I'm linked to that's going to affect my probability of getting infected in the next moment.
Absolutely. Absolutely, right. So I could be keeping track of the chance that a node with degree n is infected at time t, and that would be I'm not going to try to draw this now. It would be 1 minus S0 times theta t to the n, right? So I could keep track of that separately, and then I would get a differential equation system that has well, for every degree I would get a differential equation. Right? And so, that would be a
Mhm.
complicated system. And the elegance of doing it this way here to solve the model at the level of the random neighbor is that it's a closed system with dimension one. Right? And so the place where I'm keeping track.
I guess I'm asking about the validity of that. Should I be thinking of this as an
Mhm.
approximation?
No, no, no. This is accurate, right? And so where I'm keeping track of that is in this expectation here. Right? So the random neighbor has a random degree. Right? And so for every one of his degrees, he has a different chance of being susceptible. Right? And so then I'm taking the expectation over that, right? The theta t to the n is the chance that somebody with degree n prime has not been infected by one of her neighbors until time t.
Okay.
Right? And so then I'm taking the expectation over that. Now this is a crucial point that you're pointing out there, Evan. Yeah.
Mhm.
Maurice, one question.
Yes.
So this is a result in which you exploit the previous result, the result that as the number of agents go to infinity, all networks become a tree or can be described as a tree.
Uh, I'm going to use that on the next slide. On this slide here, I'm talking about random matching model. So I have a continuum of agents. So in that sense, but yes, I'm going to be using it in a moment.
But if you have a continuum of agents, the previous slide was talking about when the number of agents go to infinity, which is precisely what we have here.
Yeah.
So that's what
Yes.
I get. Ah, okay, I see.
Yeah. I hear you, but this is the benchmark slide, and so here
Ah,
I'm
okay,
talking about a different model with a continuum of agents.
okay.
Thank you. All right. So I'm solving the model at the level of the random neighbor here, also in random matching. And then once I've solved for that, I can solve for the infection rate of the random agent. And the only difference between the random agent and the random neighbor is that, well, the degree of the random agent is n rather than n prime. And so once I've solved for the random neighbor, I can then, in a second step, easily solve for the infection rate of the random agent. All right, so let me address the last question here on the next slide, where I am talking about the configuration network. And so the way that the configuration network is qualitatively different from the random matching is that the infections across the agents, they're correlated. And in the random matching model with the continuum population, everybody's independent. Whereas in the network, if I'm susceptible at time t, well, the chance that my neighbors are infected is going to be lower because they couldn't have caught it from me, and also I haven't caught it from them in the past. Right? So both of these correlations, they will depress the infection rate of the neighbor. right? And so when I'm thinking about the ways that I myself can get infected is, oh, man. Oh, no, 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 no. Sorry. So when I'm thinking about the ways that I'm getting infected, uh, I'm getting infected when I'm susceptible and my infected neighbor Jay gets infectious, right? So the rate at which my neighbor John is infecting me is the expectation of his of the probability that he's infected conditional on me still being susceptible. Right? So that's what I have to characterize. And the way this is richer and more complicated than the random matching model is that, well, now I have to calculate this conditional expectation. Right? And so, generically, the expectation, this expectation is, the probability that neighbor John is infected is 1 minus the probability that he's susceptible. And then I'm applying Bayes' rule here. And so to evaluate this, I have to compute the unconditional probability that I'm susceptible and the unconditional probability that both I and my neighbor John we're both susceptible. Right? The probability that I myself am susceptible in the denominator here, that's like on the last slide, and the same for all the configuration models. Agent I has ni neighbors, and he starts susceptible with probability S0, and then there's a chance theta that he's not gotten infected by one of his neighbors until time t. And so theta again is the survivor of A. You can think of A as the hazard rate and theta as the survivor of a distribution. And then the probability that I'm susceptible at time t is that I started at time 0 susceptible, and then none of my ni neighbors infected me since then. Right? So that's the denominator. Right? So that one was simple. And now comes the tricky part. What's the chance that I and J are jointly susceptible at time t? Well, okay, now I'm going to try to draw this here. How do I do this? Right, so I have Mr. I, and then I have Mr. J, and they're connected. And then Mr. I has a number of other links, and Mr. J has a number of other links. And for I and J to be both susceptible, well, they have to start susceptible, and then they shouldn't catch the infection from any one of their neighbors. I has Ni neighbors. J has
Are you
Nj
drawing?
neighbors. Say it again.
Are you drawing something?
I am drawing, yes.
Sorry, it's not visible now. Can other
Aha.
people see it?
Can other people see my drawing?
No, I can't see it.
I see. All right, so let me not try to fix this here because that's probably not going to. My screen sharing is paused. Why is my screen sharing paused? But you're seeing my slides, right?
Yeah, I see the slides.
Well, we were seeing them. I can't see them now.
I
No,
can
so-
still see them. Weird.
I still
I
see the
see.
slide that says ODEs for infection rates in undirected trees. And there's 2 revealed bullets, and it looks like there's probably something still to be revealed.
But I think it's
Yes.
frozen.
And I'm drawing again.
Hmm.
Could it
Can
be
you
that
scroll
my
to
computer's
the
not
different
frozen, right?
slide?
Excuse me?
Can you scroll to a different slide
Yeah.
just to
The,
confirm
the,
that's
the, the
frozen?
cursor's frozen in place from what I see.
Yeah.
I'm scrolling. Yeah, I'm scrolling across my slides.
Maybe you can try to unshare and reshare.
Okay. Uh, hmm. Stop sharing. Excellent. Okay, now I see you all.
Hello.
Now I see there's 30 people here. Hello. Okay, share. All right. Is this better? I'm scrolling through it.
Yeah.
Now it's working
Now
again? Okay.
yeah.
Okay, give me one. I'm going to try the annotation one more time, and And let's see whether this works. So here we have I, here we have J.
Yeah,
Is this
I
working?
see that.
Yeah. Okay, let me try my pen. Right. So I is connected to J, and then I has a bunch of other friends, and J is connected to I, and then there's a bunch of other friends and J. And so now the chance that I and J remain susceptible at time t is the chance that they start susceptible and then they don't get infected by any of their neighbors. But the key is, given that they both start susceptible, they cannot really infect each other, or they cannot leave the joint state Si, Sj by infecting each other, because the two of them, they are susceptible, right? So the only way they can catch the infection jointly is from one of their outside neighbors, right? And so how many outside neighbors do they have? So I gotta sort of click this away again here. I'm sorry, I went in the wrong direction here. So this is the undirected tree. They basically lose two neighbors, right? I cannot catch it from J, and J cannot catch it from I, and so they have only Ni plus Nj minus two other neighbors. So the chance that they're both susceptible at time t is the chance that they both started susceptible, and then they didn't catch it from any one of their Ni plus Nj minus two outside neighbors. And so now I know what the expectation of Si is, I know what the expectation of Si Sj is, and then I can plug it back into the first equation here with Bayes' rule, and this gives me a one-dimensional differential equation here for the conditional chance that J is infected in the baseline configuration model. Right, and so this now is, so we were asking before, we're talking about the finite network and then the infinite tree limit. And so this is the expression that is exactly correct in the infinite tree limit. In any given network, the reason that this equation is not altogether correct is that when I'm saying here that the expectation that I remain susceptible at time t, you got to sort of multiply up the probability that the neighbors that you didn't catch it from your neighbors. Well, here I'm assuming that they're independent. And that allows me to just multiply up these thetas across my neighbors. And so that is valid in an infinite tree network. And in any finite network, there would be correlation between the neighbors, right? And so then in any finite network, if you wanted to have the exact equation for the infection rates, it'd be a huge mess, right? So there's the so-called master equations, and the dimensionality of the master equations is exponential in the number of nodes, because everything is correlated, and you have to keep track of the joint infection state of all the agents, and that's exponential, right? So that is not practical. But in the infinite tree limit, it boils down to this one-dimensional equation. Right? And so then the approximation result, or first proposition, is going to say that this approximation is valid, that as the number of agents grows to infinity, indeed this infinitely exponentially complex master equation indeed converges to this one-dimensional equation. So this is the undirected tree. I believe, let me go forward. Can you still see the annotation? Is the annotation still there?
Yes.
Yeah, it's still there.
All right. Okay, so now, good, but I'm going to keep it for one more moment, then I'm going to delete it. So the first two blocks, they're still valid in triangle trees, right? So I switched here from undirected trees to triangle trees. But now in a triangle tree, what we're going to have on top of that is, let me annotate here, is that I and J, they have a joint neighbor K. Right? So we have this here. And now when we want to compute the expectation that that Si and Sj are jointly susceptible, well, who could they have caught it from? Well, they have their Ni friends here and their Nj friends here, but we're double counting K. Right, so K is a friend of both I and J, and when we're doing Ni plus Nj minus 2, then we double counted K, so we have to subtract one more for the double counting, and that's going to give us the formula for a triangle network. There's one more caveat, right? So the double counting, that's that's unavoidable, and that's sort of that's a feature, not a bug. There is a complication here when we're talking about the chance that I and J are getting infected from agent K, right? Because we defined here A as the chance that J is infected conditional on I being susceptible. But when we're talking about I and J getting infected from K, then we have to condition K's infection probability on I and J being susceptible, right? And so, right, so to close this here and so solve it in terms of a one-dimensional differential equation, it has to be the case that this expected infection probability of K conditional on I being susceptible is the same as the conditional probability on I and J being susceptible. Right? And so this is where we're leveraging the assumption here that when an agent gets infectious and infects a neighbor, they infect all the neighbors at the same time. Right? So that's an assumption where we're differing from the mathematical epidemiology literature. And the reason that this matters here is that when we're thinking about the infection probability of K, we're conditioning already on the fact that I is susceptible, right? So I couldn't have infected K in the past, but if I is susceptible, then J couldn't have infected K either, because if J had infected K, then given that infections are simultaneous, J would have also infected I, but we're conditioning already on the fact that I is susceptible, right? And so that's the reason that these expectations are the same, and that what we're getting here is a one-dimensional differential equation. So coming back to Evan's earlier question, what kind of model would lead to multidimensional differential equations? Well, you know, the triangular networks that the mathematical epidemiology literature has studied, where they're assuming that all infections are independent, that gives rise to two-dimensional differential equations, right? So this is where we're departing from that literature, and with that different contagion assumption here, are getting simpler differential equations. All right, so okay, with these caveats out of the way, we have the probabilities, the expectations that I is susceptible, that I and J are susceptible. We can plug it back in there, and we get our differential equation that differs from the earlier one, just because the coefficient is one less. Let me get rid of the annotations, because we no longer need them, clear all drawings. And let me summarize here. For all models, right, random matching and all the networks, the infection rate of a typical node is given, excuse me, by the same expression here, and the level at which the networks differ from each other and from the random matching model is at the rate of at the level of the infection probability of the random neighbor. Right? And so we found for random matching that was sort of the simplest expression here. For the undirected network, we saw that we have to account for the correlation between neighbors, which introduces this factor of excuse me. It introduces this correction factor of -2 here, and for triangles we saw that this correction term rises to -3. And I skipped the directed networks, but there we would find a -1. Right? So they're all very comparable, and it's clear in which way they rank. Right? So it's clear in which of these networks have the higher infection probability. Let me first take care of an earlier question about the approximation question. How do infection rates on a network converge to the infection rates on the tree? And so this here is saying that for any finite time, these infection probabilities do converge. And so why is that true? You know, we said that the trees, the networks, they locally converge to these branching processes, right? Branching process is what generates the tree, and they converge locally in the sense that, you know, for any neighborhood, the distance that I might fix, these neighborhoods converge. And then in the neighborhoods, I can use these neighborhoods to construct lower and upper bounds for all the infection rates. And these lower and the upper bounds, while they're sandwiching these infection rates, they're converging to each other, which means that, you know, whatever is sandwiched between them also has to converge to each other. It's a fairly simple argument. And so that shows that this local convergence to trees is sufficient for getting convergence of the infection rates. Right? So this is the approximation result. And with that, let me summarize our main result here for the contagion rates, and that's saying that so the twiddle here is the random matching. So random for given degree distribution, random matching has the highest infection rates. It's greater than the network, and clustering further reduces the infection rates. Right? So that's let me just sort of right into the proof is right from the ODEs, right? So they're following very similar ODEs, and the ODE for random matching is larger than the one for undirected trees, which is larger than the one for the triangle trees, because of this minus term here. Right? So we can compare them, and for regular networks, if every agent has the same degree, we get a converse, right? Because if you take the regular networks, well, then n prime is equal to n, and you can see exactly how much these infection rates of these different network and random matching models, what they differ. And so if you plug in these larger numbers, right? So if you compare, let's compare here a triangular configuration model with degree 1 larger than the undirected model. Well, that more than outdoes the advantage of the undirected network that we found there, right? So the effect of network architecture, the fact that clustering reduces contagion, it's less than 1 degree in regular networks, right? As you can read that straight off the differential equations, right? So what does that mean? The first equation means that basically social pods, yes, they're a good idea, right? So a social pod during COVID means that you're not sort of meeting random people every day, but you're committing to friends and you keep meeting them, right? So rather than bumping into random people, you interact with the same people. On top of that, if you have kids, then you sort of put your kids in a family pod where my friends meet your friends, but I'm not sort of mixing families with my friends, because that creates clustering, and clustering makes the network sort of more secluded in itself, and that reduces infection rates, right? So that's what you can read of the first equation. And then the second equation is saying that how important that is, right? So this podding to prevent the spread of the epidemic, right, quantitatively depends on the degree. Right? So if the degree is small, if we're like Kramer, we're thinking about the AIDS epidemic, and degree might be 1, or I don't know, maybe 2 or so. 1 more degree is a big deal, right? But if you're thinking about something like a cold, where I don't know what my degree is in a cold network, right? I'm sneezing at 20 people, and whether it's 20 or 21 people, well, maybe that doesn't make that much of a difference, right? So when the degree is large, the network architecture matters relatively less. Right? So that's what we can sort of read out of the converse comparative static. All right, I'm looking at the time here. I see that I'm almost out of time, but that's okay, because this really is the main result of the paper. Right, so there's sort of plenty of slides left, as you can see, right? So we do things like we study the effect of the degree distribution, right? So this is the comparative static in the network architecture. And another relevant question that we're already hinting at here is, well, what's the effect of the degree distribution? You might want to add recovery to the model, right? So that's in there. And then we have the applications where we say, well, how does sort of this ranking of contagion rates here, how does it translate into behavior, right? So in which kind of network would people be more prone to vaccinate themselves against the virus, and in which networks are they more prone to participate, to invest into participating in a helpful contagion, right? If there's an innovation that's spreading, right? And so then those models, you'll have to think about whether participation is a strategic substitute, right? So for harmful contagion, you will you might think, right? And so it's going to be true in some versions of the model that we have strategic substitutes as other people are participating, are getting vaccinated more. Well, then there's going to be less virus out there, and so there's less of a reason for me to get vaccinated, right? So that would be a model of strategic substitutes. And in a helpful contagion, you might think that this is maybe a game of strategic complements, right? If others are participating more, right? It's not, right? So in the participation model, we're thinking about individuals having a payoff from catching the infection, right? So there's no network effect in the sense that I'm benefiting from others adopting this, right? So it's just on the level of the contagion, right? Am I being reached by this, right? So that would be a model that would tend to give you strategic complements, and well, then we can think about the equilibrium participation and the welfare in these models, right? So that's the participation models, and then experimentation. So this is maybe too much history of the paper. So the way we came up with the model is from this earlier paper here, where we talk about experimentation on networks, and so that's a model where your standard Poisson Bayesian experimentation with the idea that if the product is good, then it may succeed then it will succeed if I try long enough. And when I succeed, my neighbors see it, and then they're going to sort of start trying this as well, and so eventually they're going to succeed, and then that's going to spread across the network, much like a contagion process, right? And so in that model, then we can talk about what are sort of the strategic externalities of experimentation, right? And so that also leads to strategic substitutes. So there's a crowding out going on, in the sense that if I can learn innovations from my neighbors instead of suffering through the experimentation myself, well, that's going to discourage me from innovating myself, right? So then we can talk about sort of optimal network density and in that model. So that's sort of the 5-minute flyover overview of the applications here. I'm going to end here on this slide with another quote from one of these survey papers here, that says that another limitation of the standard economic epidemiology model is that they have trouble capturing the dynamics of the epidemic, right? And so then they focus on the steady states. So here's a model that's simple enough that you can also study the dynamics. I think I'm at time, so I don't know, what's the etiquette? Okay, I'm staring at my slides, so now I'm looking at you.
If you want to, it's not like super strict. If you have something you want to finish up 1 or 2, 3 minutes, you're welcome, or we can stop here and start the discussion as you prefer.
If you give me the chance to do that, I'm going to speak for another hour, because I have enough slides for that.
Yeah,
if you talk about everything, I'll just leave it at the high level.
If we can't handle the moral hazard, then let's stop. All right. Yeah. Thank you very much. So I will first give the panelists a chance to ask any last questions or give any comments. I don't know, Sanjeev, you haven't had the chance to say anything yet. So do you want to start?
Sure. Let me. So Moritz, very nice to see you, and thank you for your talk. I finished lecturing, a bit after 4, so I only joined at 4:15. My apologies. Let me try and. So this is the first time I'm attending this forum, so I don't know the audience here, and I also don't know what my role is. But let me try and make a couple of observations. So I think it's really great that you concluded with this, with this quote from the survey. Is this the JEL survey?
Yes.
Right. Yeah. Okay, great. So this is a very good place to start thinking about, why Moritz and Simon are writing this paper. Let me make a, so it maybe I missed something, when you started, but let me go back to your proposition 2, Moritz. Maybe you could take us
Of course.
back there, the
So I
result
have
that you
to.
concluded on.
Yeah.
And so I'd make a couple of sort of high-level remarks, and maybe we can start from there. And there, as I said, I missed a fair bit of the start, so maybe you have discussed this. So I found this very interesting, and I must confess I don't. So let me try and unpack it a little bit. Okay, so and put things a bit in context. So one idea, high-level idea in this literature is that infections, the network distribution, the degree distribution is, matters for infection. And there are these famous results on how that comes into play and how it depends on whether it's a simple contagion or complex contagion and so on. So, but this result, as I understand it, is for a fixed, am I right? Is that for a fixed degree distribution?
That's for a fixed degree distribution, right? So this
Right.
is, yeah, absolutely.
So what I wanted to somehow highlight is there's a very large literature, very many of you probably are aware of this work, but there is a very large literature on how the contagion or the infectiousness of a social system is very related to the degree distribution. And
Absolutely.
there's a lot of interest in looking at scale-free versus Z-Australian.
Yes.
But this paper, this theorem actually speaks to a slightly different, as I see it, it's a different sort of concern. Here you fix the degree distribution, and you are now looking, if you like, directly, more closely at more microscopic or, more finer features of the network.
Yeah.
So yeah, which is sort of, yeah. And so let me just try and push that a little bit. So, could you say a little bit at a, at a slightly higher level about, I'm aware that you asked us to look at the ODEs, but I think let me push you a little bit to explain why, it is that the random graph, let's look at the first part of the result. So why is it that the random graph has, so as I understand, I'm not sure I totally understand. So there's this triangular random graph or triangular tree, so to say, and then you have the undirected, then the directed, and then you have the random, right? That's the order. So why is it that, could you give us some high level?
Sure.
It's a purely structural
Absolutely.
result, right? It's not about the connectivity.
Yeah, no, I mean, this basically comes down to neighbor counting, this result here. So the random matching, not so much, but the comparison between the networks, it's really a matter of neighbor counting. And so if I may go back a couple of slides where I have these trees, right? So I'm scrolling back here to, right? So you can basically see the theorem in these pictures here. And so all these trees have a degree 4.
I see.
And so how are they different? Well, the central guy always has 4 neighbors, but then look at the neighbors that the neighbor has, right? So here in the directed tree, the neighbor has 4 neighbors. Here in the undirected tree, yes, he has 4 neighbors, but one of the neighbors is just myself. That doesn't count. There's just 3 new neighbors. And so here in this triangle tree, the triangle neighbor, he really has only two new neighbors because we're not going to count this guy again, right? And so the, the coefficients in these differential equations, they're exactly counting the number of second neighbors. And that's literally where the differential equation comes from, because when you're calculating the 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 the, the infection probability of your neighbor, you're counting how many new uh, sort of links does this person have to catch the infection, right? That's how the sausage is made.
So following up on that, so there are going to be more neighbors in the directed case as against the undirected, and that's again more than the triangular.
That's right.
Neighbors or
That's
neighbors,
right.
I'm
So
sorry. Yes.
there are more second neighbors. That's right.
Yes.
And the converse result follows by the same argument, right? I mean, if you see here the directed network, it has one more neighbor. But if I increase n from 4 to 5 in the undirected network, well, then the neighbors are going to look similar. But the reason that the undirected network now is denser is that the typical node has not 4, but has 5 neighbors,
Got it.
right? So that's the converse direction. And the random matching that's different, because there it's really about the joint probability, right? So the fact that sorry for the scrolling here. The fact that random matching looks structurally the same, only with that it's yet one more coefficient here. I don't properly understand why that's true, but the math spits it out this way, right? So it's that this conditioning exactly amounts to one more neighbors.
I see.
So a way to understand the -2 here is that when I am thinking about J's infection probability, there's the reason that this chance is lower in the network rather than random matching is that, for one thing, I couldn't have infected my neighbor. That's -1. But then also my neighbor couldn't have infected me in the past.
Mm-hmm. Mm-hmm.
And that's 2, right? I mean, so that sounds a bit cheap, right? That sounds like a heuristic, but the math spits it out exactly.
So let me. I'm conscious that I shouldn't, monopolize things. So let me just push you a little bit. So a major sort of, from a policy side, I think you again may have spoken about it in your talk and I missed it. But from the policy side, a major concern has been how do you intervene, to control these things spreading.
Yeah.
And you could have what is known as, if you like, random vaccinations, or you pick at random, or you target. And I was just wondering whether, again, those results are usually take the form that, if the graph is very sort of like an Erosh-Renyi graph, it doesn't probably matter very much which way you go. But
Yeah.
if it's scale-free, or power law, then it really matters whether you do random or you do targeted vaccination. But I was wondering, have you, you said there's other things you've done. I was just wondering if you had thought about, how your methods could help us, address those kinds of questions.
So the model speaks, of course, to the degree distribution, right? So I mean, here I'm presenting the result on the comparative static in network architecture, the type of the links rather than the number of links. But clearly the model can speak to the comparative static in N. So I believe that's the next slide here. So I'm just going to unstrip it all here. So the reason I didn't emphasize it so much is that basically we're rediscovering what the random matching epidemiology literature has found. So clearly, if you have more degrees, that's going to infect faster. Maybe surprisingly, the first order stochastic dominance increase is not going to do it because the first order stochastic dominance isn't inherited by the neighbor distribution. So, but MLRP increases are. Okay, so that's maybe more of a technical point. So yes, if you have more degrees in that sense, that's going to accelerate the contagion, not surprisingly. A mean preserving spread. So you have super spreaders now. So it has been emphasized, of course, that this can accelerate the contagion because there's there's basically a square term in the contagion model, right? So it's my infection, my sociability times your sociability that's driving the infection, right? And so that's why so this multiplication is a complementarity that means that these high degree nodes they're overly important, right? And so the way the model picks it up is that if I increase, if I have a mean preserving spread, that increases the degree distribution of the random neighbor, right? And so that drives up the infection rate there. So formally, it's true that for T small, initially these infections they follow an exponential path. So initially, this is going to increase the infections, and so there's these famous results out there that say that if you have super spreaders out there, then no degree of vaccination except for 100% is going to stop this, and that's true. That's true here, and it's true in the networks, and it's basically because the neighbor has the expected degree of the neighbor can be infinite, right? And so then there's no way that this guy is not going to catch it, right? And so that's going to make it take off immediately. And there's a converse to that, which is also known in the literature, but maybe less known, which is that in the long run, a mean preserving spread is actually bad for the contagion because, in the short term, it's the super spreaders that accelerate the contagion. But in the long run, it's the low degree agents. With a mean preserving spread, you have more low degree agents, and they have a chance of just sitting on an island that didn't get infected, and then they're not going to catch it. So for large T, it's not literally a mean preserving spread, but it's the minimum of the degree distribution that is determining the long-term infection rates. And so there is a flip side to it. But all these results, they're true also for random matching, and they're kind of known for random matching. So that's why we're not pushing it this much.
Thank you. So
Thanks very
we're
much.
running up against the official end before I've even gotten to Evan. So maybe we stop the official part, and Evan, if you still have a minute and you have any comments, or do you need to rush away immediately?
I guess I would just ask if you have sort of some sense of how. So if you could go back to proposition 2.
Just a sec. Okay, we stop the recording and then we can continue with the discussion. So so I say officially.
Yeah, I'll just hopefully this is brief, but I guess it's my sort of one question. So like looking at this, you sort of have this